So we've done, excuse me, the electron geometries and the shapes of molecules. We can now come back to skeletal structures and talk a little bit more about them. And if you remember, we showed this skeletal structure before, and this is the skeletal structure for prednisone. And we can start to interpret more about this Lewis structure, or sorry, the skeletal structure. So first off, we're getting more and more used to seeing the oxygens. Now we've got some double bonds. We're now been exposed to the fact that this is an out wedge. That means from this carbon right here, it is attached to 3 other carbons, and then one of them is, the 4th place is coming out of the page to another carbon. And that carbon, since it's not attached to anything else, has 3 single bonds to other hydrogens. And I've just trying to draw them in there anywhere they could fit. We see that we've got an up wedge and a down wedge to hydrogens here. And what we said was for skeletal line bond structures, you don't often, or you don't ever draw the hydrogens, but that was not true. We're seeing some hydrogens here, and that's because these are important, of course. And so, but why are they important? Well, these carbons have 4 positions, and if the hydrogen was, instead of an up wedge or an out wedge, it was a down wedge, it would not be the same molecule. Because you can see there's only 1 hydrogen to each of these. And what this is called is, so if this is called a chiral carbon, actually it's not called a chiral carbon, actually it is called a chiral carbon. And so if the H is on a down wedge, or both of these H's are on down wedges, that is a different molecule. And the details of that are beyond the scope of this class. What is within the scope is that we can look at some of these carbons and tell whether or not they're tetrahedral, trigonal planar, or other electron geometries. If we go to this carbon right here, we know it's a carbon because it's not noting, so it's just a point or a crossroads, if you will. There are 1, 2, 3, 4 different bonded atoms to this carbon. This carbon is tetrahedral. So, and what we might say is it has 4 electron groups. It is tetrahedral, it has sp3 hybridization, and what else can we say about it? Oh, bond angles 109.5 degrees. Okay. And that's clearly got 4. So this carbon right here actually has 1, 2, 3, 4 bonds. With 4 bonds but 3 electron groups. We know that this carbon right here is going to be trigonal planar, sp2 hybridization, bond angle 120 degrees. Trigonal planar, 120 degree bond angle, sp2 hybridization. And so this bond angle is 120. Now let's see. Carbon over here has 1, 2, 3 bonds shown, and any bonds not shown are 2 hydrogens. You can draw in the hydrogen if it helps you. And for me, I can see that there's 1, 2, 3, 4 bonds for 3 electron groups. So this carbon right here, also trigonal planar, 120 degrees, sp2 hybridized. And it turns out that in this molecule, there are only 3 electron group carbons and 4 electron group carbons. And so those are your only 2 choices, is sp2 hybridized or sp3 hybridized. And you could go through for each of these and show what kind of hybridization, what kind of electron geometry each of these has. That's why the electron group idea is so powerful. Is not only, so first of all, you can do it for any carbon. You can also do it for other elements as well. Should there be other elements that are central atoms, because we will only do electron geometry for central atoms. That means atoms that are surrounded by two other atoms, so that we can determine the geometry.